Welcome to another video. Here, we are moving from developing the mechanics of simple linear regression, such as estimation and interpretation, into the next phase of analysis, which involves inference, diagnostics, or applications. Specifically, we will cover the properties of least squares estimators in simple linear regression and talk about how to use these properties for running hypothesis tests on these estimators. Up to this point, we focused on how to compute these least squares estimators and how to interpret them. Now we turn to understanding their behavior as random quantities. Because the regression coefficients are computed from sample data, they are themselves random variables. This means they have properties such as an expected value and a variance. Under the standard assumptions of simple linear regression, including linearity, independence, constant variance, and normally distributed errors, the least squares estimators have very desirable statistical properties. In particular, the estimator for the intercept and the slope are unbiased, meaning that, on average across repeated samples, they recover the true underlying parameter values. In addition, we can explicitly describe how much variability these estimators have, which allows us to quantify uncertainty, construct confidence intervals, and perform hypothesis tests. The standard error is simply the square root of the variance, but it plays a more practical role. While variance is measured in squared units and is harder to interpret, the standard error is expressed in the same units as the estimator itself, making it easier to understand and use. The standard error is what appears in regression output and is used directly to construct confidence intervals and perform hypothesis tests. Returning to our example, we consider a chemist who is producing oxygen through a complex chemical process. Based on 20 experimental runs that have already been conducted, the chemist knows that the purity of the oxygen produced depends on the level of hydrocarbon present in the raw material. Our goal is to determine whether these prior observations can be used to construct a simple linear regression model that estimates the oxygen purity before running a new experiment. Looking at the results on the right, we can see that in addition to the reported beta-0 hat and beta-1 hat values in the coef column, Python reports the standard error values for the least square estimators. As mentioned earlier, knowing the standard errors allows us to quantify uncertainty and perform hypothesis tests. Suppose we want to test whether the intercept and the slope are equal to some specified constants. In practice, this often means testing whether a coefficient is equal to 0, which corresponds to asking whether that term has a meaningful effect on the response variable. For each coefficient, we set up a pair of hypotheses. The null hypothesis states that the true coefficient equals the hypothesized value, while the alternative hypothesis states that the true coefficient is different from that value. To carry out the test, we compute a t-statistic by comparing the estimated coefficient to its hypothesized value and scaling by its standard error. Under the assumptions of a linear regression model, this test statistic follows a t-distribution with n-2 degrees of freedom in simple linear regression. The figure on the right illustrates this t-distribution. The center region, labeled 1-alpha, represents values of the test statistic for which we fail to reject the null hypothesis. The two shaded tails, each with area alpha divided by 2, represent the rejection regions. If the calculated t-statistic falls into either tail, we reject the null hypothesis and conclude that the coefficient is statistically significant. Returning to our example, we now perform hypothesis tests on the intercept and slope to determine whether these parameters are statistically significant. From our earlier calculations, we already have the estimated values of beta-0 and beta-1. In addition, we have the sum of squared deviations of x from its mean, also known as SXX, and the estimated sigma squared, which together allow us to compute the standard errors of the least squares estimators. For the slope, we conduct a two-sided hypothesis test, where the null hypothesis states that beta-1 equals 0. To construct the t-test statistic, we subtract the hypothesized value of 0 from the estimated slope, which is 14.95, and divide this difference by the standard error of beta-1. This results in a t-statistic of 11.352. Since this value lies within the rejection region, exceeding the critical value of 2.10, we reject the null hypothesis and conclude that the slope is statistically significant. Similarly, for the intercept, we conduct a two-sided hypothesis test, where the null hypothesis states that beta 0 equals 0. We compute the t-statistic by subtracting the hypothesized value of 0 from the estimated intercept, which is 74.28, and dividing by the standard error of beta 0. This yields a t-statistic of 46.62, which is also well within the rejection region. As a result, we reject the null hypothesis and conclude that the intercept is statistically significant. Returning to the Python results, we can see that the same section of the output reports the corresponding t-test statistics and their associated p-values. It is important to note that the OLS model, by default, performs hypothesis tests on the significance of both the slope and the intercept. Given the very small p-values reported in the output, we conclude that both the slope and the intercept are statistically significant. Interestingly, we can compute the t-test statistics for both the intercept and the slope directly from the reported regression output, using only the estimated coefficients and their corresponding standard errors. For beta 0, we subtract the hypothesized value of 0 from beta 0 hat and divide the result by the standard error of beta 0. This gives us the t-test statistic for the intercept. Similarly, for beta 1, we subtract the hypothesized value of 0 from beta 1 hat and divide by the standard error of beta 1, which gives us the t-test statistic for the slope. But what about the p-values? Can we determine the p-values associated with these t-test statistics? Please pause the video here and take a moment to think about how these p-values might be computed. The answer is yes, we can absolutely estimate the p-values once we know the t-statistics and the degrees of freedom. Because we are working with simple linear regression using 20 observations, the t-test statistics for both the intercept and the slope follow a t-distribution with 18 degrees of freedom under the null hypothesis. To obtain the p-value for a two-sided test, we calculate the probability of observing a t-value whose absolute value is at least as large as the one we computed. For very large t-statistics, such as those we obtained for both the intercept and the slope, the corresponding tail probabilities are extremely small. This means that observing such extreme values under the null hypothesis is very unlikely, which leads to very small p-values. Thank you for watching. I hope this video was helpful, and I look forward to seeing you in the next one.